Okay, welcome back. Let's do the next one in aircraft fuel systems. This is going to be a little bit of an overview, fuel system design. So let's hop right into it. Let me position myself a little bit. All right, I guess that's fine. All right, here's an illustration of a typical fuel system in a multi-engine aircraft. You can see the engines, the left main and the right main at the top of the screen. And you have various manifolds that are either delivering the fuel to the engines, the green manifold piping type system that is used in effect by all of the white boxes, which are the separate fuel cells or the fuel tanks. And you can see that basically any fuel tank can service any engine, including the smaller APU engine in the back. Design and performance improvements in aircraft and engines have increased the demands on the fuel system. Fuel systems in today's aircraft are more complicated, and a corresponding increase has occurred in installation, adjustment, and maintenance challenges. To ensure safe operation, certificated aircraft must meet the stringent requirements established in 14 CFR Part 23. And the fuel system is in the, you can see the subpart there. We talked briefly about the manifold cross feed fuel system. It was basically the one manifold which allows any fuel tank to service any engine. Another characteristic is that all the tanks can be serviced through a single refueling spot. And you can see down here there's an underwing refueling receptacle. And basically that receptacle can fill each of the tanks. And we already said any engine can be fed from any tank. That way the pilot can balance the fuel load and not have to drain number 3 for the number 3 engine for whatever reason. 3, all engines can be fed from all tanks simultaneously. So engine number 3 can receive from all, in this case, all 5 tanks. And number 4, a damaged tank can be isolated from the rest of the fuel system. So let's say you got a damage in number 4, you can basically shut that one off and not affect engine number 4. One of the more early elementary types was the gravity feed system. You can see there is no fuel pump. Basically, the tanks are located high in the aircraft, usually in the wings. And you can see the feed system relies a little bit on gravity. So the fuel goes down through a selector valve, and it's eventually going to get to the engine back here, but it's basically all a downhill type flow. You can see there's a strainer, a drain, and a primer, which we can talk about in a little more detail. These are common in the high-wing aircraft with a fuel tank in each wing. Our Cessna 150s, you'll see, are this way. The space above the liquid fuel is vented. You can see the two little vents. That maintains the atmospheric pressure on the fuel as the tank empties. You don't want those clogged up, otherwise the fuel will not flow. For gravity flow systems, the fuel flow rate must be 150% of the takeoff fuel consumption of the engine. So the carburetor requires 10 units of fluid per second. This system has to be enough to provide even 15 units per second. So 150% of what is the takeoff requirements of the aircraft engine. The two tanks are vented to each other so that there's no change of pressure between the two. A single screen outlet on each tank, feed lines that connect to either a fuel shutoff valve or a multi-position selector valve. In this case, it's to a selector valve. Downstream of the shutoff valve the shutoff valves are upstream. So the fuel selector valve is here. I guess the shutoff valves are not shown in this illustration. The fuel passes through a strainer. This often has a drain function to remove sediment and water. From there it flows to the carburetor or to the primer pump for engine starting. Now keep in mind there is a little pump, but it's more of a push. So you're going to kind of pump it up a little bit with your thumb. And for start, that helps. It does deliver extra fuel to the carburetor. Having no fuel pump, the gravity feed system is the simplest aircraft fuel system. Question comes up. A typical large aircraft or large transport aircraft fuel manifold system allows how many of the following? 1. All tanks can be serviced through a single connection. I like that one. So far 1. 2. Any engines can be fed from any tank. I like that one also. So 2 so far. 3. All engines can be fed from all tanks simultaneously. That was also on the list. So far it's going to be 3 or 4. And 4, a damaged tank can be isolated from the rest of the fuel system. So basically, it just read down the requirements of CFR 43. So 1, 2, 3, and 4. All of the above. What precautions must be observed if a gravity feed fuel system is permitted to supply fuel to an engine from more than one tank at a time? What little precaution if you're going to have a single engine receive fuel from both tanks at the same time? I'll make sure that pressure is going to be equalized. So how would you do that? A, the tank airspaces must be interconnected. Well, that's probably good enough right there. B, the fuel outlet ports of each tank must have the same cross-sectional area. C, each tank must have a valve in its outlet that automatically shuts off the line when the tank is empty. Neither B or C really address what they're talking about as far as the precaution would be that the tank airspaces must be interconnected to equalize the pressure. So you're not going to have little pressure from one tank and a lot of pressure from the other. And it's also required by the CFR. The fuel filler cap. The neck and cap are usually in a recessed well equipped with a scupper and drain. Scupper, you can see the definition there. It's a little bit of a recess so that it is collected and it finds its way back into the fuel tank. Fuel caps have provisions for locking devices to prevent accidental loss during flight. Yeah, the last thing you want is your fuel cap to come off during flight and fuel start draining out. So they lock pretty good, actually. As you can see, you rotate it and then you put the little part that you're turning, it recesses back into the top. So lightning safe fuel caps are often installed in aircraft that fly in all types of weather. You certainly don't want lightning to hit your fuel tank. Something could happen there. So these caps have no metal exposed on the inside of the tank and will not conduct the lightning charge to the fuel. Even the lanyard that prevents the tank cap from being misplaced. Do we see the lanyard? A little bit. You can see the chain here. That's the lanyard. Even that must be made of a strong, non-conductive plastic type material. Large amount of data gathered from airplanes in service constitutes an important source of lightning strike protection information that Boeing uses to make improvements in a lightning strike damage control that will reduce significant lightning strike damage if proper maintenance is performed. You can see the regulation 23.954. The fuel system must be designed to prevent the ignition of the fuel vapor within the system by direct lightning strikes or swept lightning strokes or corona or streaming at fuel vent outlets. So lightning protection on airplanes may include wire bundle shields, ground straps, composite structure, expanded foils, wire mesh, embedded metallic wire, and similar coverings. Basically, we're going through some of the requirements under 23, the 900 series, which covers aircraft fuel systems. Because the questions are geared towards them. Here's a newer question. A fuel system must be designed to prevent fuel vapor ignition caused by what? Well, we just read it. It's not overheating or backfire. It is lightning. Filler openings, it looks like we've got a continuation. This one's well beyond the 900s. This one's 1550. It has more to do with placards, basically, or the markings, basically the writing. And if you're going to fuel the aircraft, you want to make sure that you're putting in the right fuel. In this case, it's avgas minimum grade 100 LL, which you can even see it's got the blue color for 100 LL or the green 100. And it's got some information as to the maximum capacity of the fuel cell, and in this case it's the usable fill it right up to a tab, which when you open it up you can see it. So basically the requirements of the FAA are that at or near the filler cover you have the word avgas. Okay, that's correct, it does. And the minimum fuel grade, there it is, minimum grade. If it's a turbine-powered aircraft, it's got to have the word jet fuel. Maybe I have that on a different slide. If it's pressure fueling systems, there's also going to be the pressure marking. Oil filler openings have similar requirement for markings or placards. It'll have to say the word oil. So you, and coolant has its own marking also. So you don't, uh, when servicing, you're not interchanging your fluids. Here's the jet fuel showing jet fuel only, and what else was there? The permissible fuel designations are referenced to a flight manual. This one here, see the airplane flight manual. There's a number of jet fuel. Usually Jet A is what is going to be used here, but here's one that allows, this one's an oddity. Jet A, Jet A1, Jet B, JP4, JP5, JP8, or equivalent. And because of the pressure fueling, it does have the maximum fueling pressure and a much lower defueling pressure. According to Part 23, what minimum required markings must be placed at or near each appropriate fuel filler cover for reciprocating engine-powered aircraft? Okay, well, you don't want to see Jet A if it's reciprocating. The word avgas, so far, A and C look right. And the minimum fuel grade, that looks good. And, or C, the word avgas and the total fuel capacity. According to 23, it was avgas and the minimum fuel grade. One of these questions might be, let me see if it's in this section. There was a beware on this, though. What minimum required markings must be placed at or near the appropriate fuel filter cover on utility category aircraft? Okay, here we got avgas, the minimum grade, and the total tank capacity. And on C, we just see avgas and the minimum fuel grade. So far, that sounds like the best answer. You know, sometimes they might say the total fuel capacity. We saw that it said it on one, but it wasn't required by the regulation. And this other one here, a designation for the engines and the usable fuel tank capacity, also extra. So I'm going with C. Oh yeah, the one to look out for. This one here says you have to include the words jet fuel, and I don't believe that was correct. Let me go back and read what it said. Oh, it does say jet fuel. All right, my bad. Jet fuel and the permissible fuel designation. So, what markings must appear near the filler opening of the fuel tanks on reciprocating engine-powered aircraft and on a turbine-powered aircraft? So you're kind of getting a double oral question there. Certainly answer the reciprocating. That might be enough. Avgas and the minimum fuel grade. If you remember the turbine, it's going to be jet fuel. Now this is one where I think the answer might not agree. And the various grades or the reference to the flight manual. All right, and here it is. Reciprocating, yes. Avgas and the minimum grade of fuel. Turbine, the word jet fuel. All right, I corrected it. That's what happened. I think wherever I got this, the editor's answer wasn't exactly accurate for a turbine. This one's a little closer to the regulation. Routing of fuel lines. In this case, I'm looking at a hydraulic line, but it's basically the same for other fuel lines. Basically, the liquid is over the wire. Is that the case? Let me see. Aerospace, the wire is supposed to be above the fuel. Oh, okay, this is maybe it's an optical illusion, but I kind of thought that was wrong. If it is impossible to physically separate fuel lines from electrical wire bundles, locate the fuel line below the wiring. Yeah, so if the fuel leaks, it's not going to leak on the wires. Okay, so this picture is wrong. The caption is correct. It is never permissible to clamp a wire bundle to a fuel line. Certainly don't clamp them together. If there's going to be a bend, you're going to, basically you have to bend it in order to relieve possible stresses on it. In a situation like this, any little deviation is going to put stress on the fuel line and probably create a leak, as opposed to this type of configuration where there can be movement between the top and the bottom, and there's going to be enough bends in there, 1, 2, 3, 4, to basically absorb any misalignment or vibration, expansion or contraction. The flexible hose, as shown below, should never be stretched tightly between two fittings. You can see that one's wrong. You always have a little bit of a joggle in it. When routing a fuel line between two rigidly mounted fittings, the line should A, have at least one bend between such fittings. Now this one's a rigid line, so it's not the flexible line. So how many bends? Or B, be a straight length of tubing and clamped to the aircraft structure. Doesn't sound very good. Or C, have a flexible line added between the two metal lines to allow for ease of installation. Yeah, I wouldn't say that makes it any easier. And of course, the ease of installation is not the designer's top priority. So basically, the easiest answer is A, have at least one bend between such fittings. If a fuel line and an electrical wire bundle are parallel to each other, what's the rule? Fuel line and the wire bundle should be on the same level, fuel line should be above, or the fuel line should be below. Think of the fuel dripping. Where would you prefer? You'd prefer it to be below C. Static electricity will build up. I think we talk about little bonding jumpers in a number of classes. So you're going to get a little touch of it here in fuel systems also. Metal fuel lines and all aircraft fuel system components need to be electrically bonded and grounded to the aircraft structure. That's important because the fuel flowing through the system, just the fuel movement, creates static electricity, and that little bit of electricity has to have some place to bleed off rather than build up. It's commonly done with bonding cushion clamps, shown in the top. And let's see. I think that's all you need to worry about there. Question. Fuel system components must be bonded and grounded in order to A, drain off static charges. Sounds good. B, prevent stray currents. Or C, retard galvanic corrosion. All right, basically it's the static electricity is why we bond items and ground them. Because static electricity could spark and cause a fire. A fuel strainer It's essential that the fuel supplied in aircraft engine be free of contamination. Because of this, every aircraft fuel system requires a series of strainers and filters. In addition to strainers, there must be a provision for draining a sample of fuel from all the tanks and from the main strainer. This is to examine the fuel for the presence of any water or solid particles that could have been condensed in the tank or been introduced during the fueling. You might see the word here, a gasilator. It's the main fuel strainer. It's between the fuel tanks and the fuel metering device on many light aircraft. And you'll see this in the shop where you safety wire the bottom. After you put the thumb nut back, you safety wire the bottom to the top so that it doesn't rattle open. You can see there's a transparent bowl, there's a screen which could be cleaned or replaced. The fuel comes in, the fuel goes out. The primer is also attached to it. There must be a fuel strainer for the fuel tank. These are often the finger strainers that are shown. On reciprocating engine aircraft, the strainer must have 8 to 16 meshes per inch. In addition to fuel tank strainers, there must be a fuel strainer or filter between the fuel tank outlet and the inlet of either the fuel metering device, the carburetor, or an engine-driven positive displacement pump, whichever is near the fuel tank outlet. Which is a concept that's going to be one of the more important for this class, but we're not quite into it yet. We're still talking about the strainer. Why is the main fuel strainer located at the lowest point in the fuel system? A, it traps any small amount of water that may be present in the fuel system. So far, not too bad. B, it provides a drain for residual fuel. The drain part's right, but not for the residual fuel. Or C, it filters and traps all microorganisms that may be present in the fuel system. Well, if it didn't say, it's a toss-up between A and C. So is it mostly for the water, or is it also for the trapping any of the microorganisms, or is it for both? I don't vividly remember the answer, but I believe it's because of the location so that you can drain off the extra water. The fact that it filters and traps all microorganisms, I do not like the word all there because there's going to be a milli-microorganism that's not going to be trapped by a fuel strainer. So I'm going to go with A, but I could see if it was, yeah, it is A. Where are the fuel system strainers located? Well, it ties in with the last question. Ordinarily, well, between the fuel tank and the fuel metering device, ordinarily at the lower part of the system. One strainer is located at the outlet of the tank, and the main strainer is located in the fuel line between the outlet of the fuel tank and the inlet to the fuel metering device. All right, it's probably good that I said a few extra words. I probably would have gotten credit, even though I may not have answered it as precisely as the suggested answer. Although I wasn't wrong. 23.967 fuel tank installation. I think there's a question that comes up about these ferry tanks, and you can see I've got a picture of someone that's carrying an extra fuel tank. Some of these planes, you're island hopping. Okay, here it is. For example, an aircraft with only a 1,000-mile range to be delivered from North America to Hawaii which is over 2,000 miles away, that aircraft will require a ferry tank to supply it with enough fuel to travel the excess miles. So I'm sure that's a great feeling right there. You go ahead and fly this aircraft from California to Hawaii. Make sure you carry an extra 1,000 miles worth of fuel. Why am I talking about this? Fuel tank should be supported. Each fuel tank compartment must be ventilated and drained. No fuel tank may be on the engine side of the firewall. There must be at least a half-inch of clearance between the fuel tank and the firewall. No part, this one is clearly in the back seat, so it's not up by the firewall. And no part of the engine nacelle skin that lies immediately behind a major air opening from the engine compartment may act as the wall of an integral tank. All right, let's see what the question is. What's the minimum distance allowed between a fuel tank and the firewall separating the engine? Okay, what was that? 1/2 inch, right? A. Here's the fuel tank vent. This vent line is at the highest point of the fuel tank next to the fuel cap. To allow proper fuel flow, each fuel tank must be vented from the top part of the expansion space. They must be located and constructed in a manner that minimizes the possibility of being obstructed by ice or other foreign matter. And the venting capacity must be enough so that it allows the rapid relief of excessive differences in pressure, which a larger diameter tube will do that. The airspaces of the tanks must be interconnected. Outlets must also be interconnected. Okay, we already saw that rule. All right, what is one purpose of a fuel tank vent? Is it to maintain atmospheric pressure? Yeah. B, to decrease fuel vapor pressure. Or C, to decrease tank internal air pressure. That one might be right too. To decrease. All right, another trick question for me. I'm going to go with the atmospheric pressure, but maybe I've read this stuff too much. I can see where C might be a little more direct answer, but let's see. It is atmospheric pressure. Part of the reason is that C isn't exactly right because it could increase or decrease. I mean, the opposite could be required. Why is it necessary to vent all aircraft fuel tanks? Is it A, to ensure a positive head pressure for a submerged boost pump? Or is it B, to exhaust fuel vapors? Or is it C, to limit the pressure differential between the tank and the atmosphere? All right, the other two answers are, they sound good, don't they? But because we've been studying vents, we realize that the only reason we have a vent is to worry about the pressure difference between the tank and the atmosphere, or the atmospheric pressure, or whatever. So C is going to be our best answer when we see the vent word. Um, 23.953 requires fuel system independence. If the single fuel tank or series of fuel tanks interconnected to function as a single is used on a multi-engine aircraft, the following must be provided. 1. Independent tank outlets for each engine, each operating a shutoff valve at the tank. This shutoff valve may also serve as the firewall shutoff valve required if the line between the valve and the engine compartment does not contain more than 1 quart of fuel. Basically, the aircraft are going to have both. You're going to have you have usually an overhead valve for each of the fuel tanks, and you also have a firewall shutoff valve. At least 2 vents arranged to minimize the possibility of both vents becoming obstructed simultaneously. Air vents. Fuel tank shutoff valves have 2 positions, open and closed. And you can see a few on the screen. The question is, how many vents arranged so that they are not likely to become plugged at the same time must be used in multi-engine fuel systems? So how many vents? Did we see the answer in there? I'm going to say 2. Did we see that? Yeah, they must have 2 positions, open and closed. That doesn't totally tie in. At least 2 vents arranged to minimize. Okay, so there you go. At least 2 vents. A. Okay, we've got a review video, which I haven't gotten authorization for yet. Hopefully it's going to be posted. If not, if you do have the videos, you can see the timestamp of the review on there. What are we looking at? 37 minutes. Let me go a little bit further just to wrap up this class, maybe another 7 minutes or so. There's a regulation on fuel tank expansion space. Each fuel tank must have an expansion space of not less than 2% of the tank capacity unless the tank vent discharges clear of the airplane, in which case no expansion space is required. It must be impossible to fill the expansion space inadvertently. So you can see they can't actually fill it up by pouring more fuel in, because it's only going to go, apparently it's only going to go to this part. There's always going to be a vapor head space there. Each fuel tank must have an expansion space of not less than what percent of the total tank capacity? That was a 2%. Each same question, 2%. Some type of screen is used to capture contaminants attempting to flow out of the tank into the fuel system. Finger screens are common. They effectively increase the area of the fuel tank outlet because they're so long. That allows a large amount of debris to be trapped while still permitting fuel to flow. You don't want just a screen because it clogs up awful easily. A long finger, if this one's clogging up here, there's still going to be enough fuel flow through the other side and part of this side. On light aircraft, this type of strainer is commonly used at the fuel tank outlet. It's not that gascolator. We saw what that was. That has to be safety wired. But at the fuel tank outlet, the finger strainer is what we normally see. If you're going to be checking for fuel system contaminants, it requires continuous vigilance. Certainly your fuelers are going to be particularly aware of that. Daily draining of strainers and sumps is combined with periodic filter changes and inspections to ensure the fuel is contaminant free. Here's an example of a sump drain tool. Strainers and sumps should be drained. How often? Daily, weekly, after every 100 hours of flying time, or after every 100 hours of flying times. Did I say that right? Uh, Sounds like 100 hour, but let me go back and what did it say? Daily sump draining is part of the procedures. All right, this is something pilots do. Um, yeah, okay. Yes, they do that daily. That's one of the first things the pilots do. They pull out the sample, they bring it into the hangar, they dump it into our fuel dump, and they do that daily. I'm mostly looking for any little bit of water that it's accumulated. So daily. Yeah, sorry, I didn't quite understand the question at first. All right, here's what a regulation looks like. These are the CFRs. They're the Code of Federal Regulations. For those that really care where that comes from, Congress passed a law that basically is under 14 aerospace and aeronautics and space, and they have a bunch of the overview, and they also authorize regulations. So that's why the regulations ties in with the same um, section or U.S. section of the statute. So in this case, it's 14 aerodynamics in space, and this one's parts 1 through 59. Right now, we're looking at part 23, and that's fuel system requirements. Each fuel system must be constructed and arranged to do a number of things. So the requirements of the fuel system in a normal category aircraft is found in what? 14 CFR part, it was 23. The fuel flow requirements, we already saw that if it's gravity fed, the fuel flow must be 150% of the takeoff fuel consumption. And there's also a similar requirement for pump fed systems. It's a little lower, 125% of the takeoff fuel must be able to be flown. And then for turbine engines, it must be at least 100% of the fuel flow required by the engine under each intended operation condition and maneuvers. So you're not required to have the additional 50% safety factor on a turbine engine, or the extra 25% from a pump to a gravity feed. A gravity feed fuel system in the normal category airplane must flow what percentage of the takeoff fuel flow to the maximum power approved for the engine? Gravity fed was 150%. Do we have the same question for the other ones? What is the requirement for a pump fed system? 125. What about for a turbine? 100. Most large multi-engine aircrafts incorporate some form of A, independent tank the engine fuel system. Kinda, maybe. Let me think about that. B, manifold cross feed fuel system. Oh, much better answer. Or a C, a gravity fed fuel system. Well, definitely not for a large multi-engine. It would be a manifold cross feed fuel system. And there's a definition right there. We looked at that earlier. The area around the fuel tank filler of a small reciprocating aircraft must be marked with the word avgas and the minimum fuel grade, A. Turbine engine fuel filters. Another type of filter that is widely used for turbine engine fuel systems is the wafer screen filters shown. And here's the wafers right there. The filtering element is a stack of wafer-type screen discs made of 200 mesh bronze, brass, or stainless steel wire screen. This type of filter can remove very tiny particles from the fuel and at the same time can withstand the high pressures found in a turbine engine fuel system. Some of the fuel filters used in jet transport aircraft have a pressure switch across the filtering element. If ice should form on the filter and block the flow of fuel, pressure drops across the filter will increase enough to close the contacts and turn on a light in the flight engineer's panel, warning that ice is forming on the filter. Probably more information than you need. Question. The fuel filters in some turbine engine aircraft are fitted with a pressure switch across the filtering element. The switch turns on a warning light on the flight engineering panel if there's some ice. The filter should clog because of ice. And also B, pressure across the filter should drop. So I was gonna say they're both probably right. I'm not sure what the book said. I'll have to see if I can even find this question again. All right, that's going to be plenty for now. 46 minutes. Just a minute or two before break. So, all right. I think we wrapped it up pretty nicely there. So, let's go ahead and take your break, and I'll see you at the next session. Bye.